Yeah, I'm going to talk about variational filtering, and I'm going to skip the first two slides because they're too controversial. So basically, the algorithm is in the intersection of dynamic systems, deep learning, and statistical inference, especially expectation maximization, variational inference. So the statistical inference part makes the whole thing completely unsupervised. The dynamic systems part provides basically the structure of the model. So we are modeling NILM as a dynamic system. And then the deep learning part is basically the optimization engine of the whole thing. It makes it pretty fast. Depending on your background, I would summarize the algorithm differently. If you are a statistician, I would say it's expectation maximization, but we have a new network that tells us where to look for probability mass. If you're a machine learning researcher, I would sell it as like an unsupervised deep neural network that learns to perform posterior inference. And if you're from the dynamic systems community, I would say it's a nonlinear Kalman filter that is unbiased and is pretty fast because of the neural network. And this is basically the angle of attack. So we're going to start out with the statistics part, go over to the deep learning part, and then the dynamic systems part. And I'm going to heavily make use of two techniques. One of them is Monte Carlo integration, which basically just means you can approximate an expectation by sampling. And the second one is importance sampling. And importance sampling basically means if you have an expectation with respect to one distribution, you can change the distribution, but you have to account basically for the bias that you're introducing. And importance sampling works. So this is a strict equality, so importance sampling is unbiased. But basically, the closer Q is to P, so Q is the distribution that you're sampling from, and P is the true distribution. The closer Q is to P, the lower the variance of the estimator. We're going to make heavily use of the fact that we're going to have a distribution Q that is close to P. So this is basically expectation maximization in one slide. So EM is a technique to perform maximum likelihood inference on parameters theta in a latent variable model. And it's unsupervised because we only assume to have observations. And the latent variable in this case is Z. And it's a binary vector that tells us whether or not appliances are on or off. So Z is a vector. And if you do EM, you can basically show that you're doing coordinate ascent on this function f. And basically in the E step, you're computing some distribution P. And basically what you're computing is the posterior. And in the M step, you're increasing the log likelihood. So basically if you plug in the posterior for P, this just becomes the data log likelihood. So what are the parameters theta? So basically in the case of NILM, the distribution of X, like our observation given the latent variable Z, you can just model that as a Gaussian. And then basically, depending on your data, it's either the reactive power and active power, if you have like two-dimensional observations, or you could have like waveforms. And we are using waveforms, so this is basically the theta that our algorithm came up with, and those are the waveforms of the appliances that the algorithm detected. Yeah, and expectation maximization allows for learning theta, so we don't assume we know theta. Like in the slide before, if you want to perform coordinate ascent on this function f, you need to compute the posterior. And for many interesting problems, computing the posterior is intractable because you need to compute p of x given theta, and that basically requires a summation over the latent space, and that's just intractable. And NILM is one of those problems. Basically, because z is a binary vector, basically the domain of z grows exponentially with the number of appliances. And basically, variational inference is one technique to deal with, basically, it's a generalization of expectation maximization where you assume that you can't compute the posterior. And basically what you do is, it's the same function. But instead of computing the posterior, you introduce an auxiliary posterior that is parameterized by psi. And then basically you are turning statistical inference into an optimization problem. So basically instead of coordinate ascent, where you would compute the optimal p tilde, you just assume you have like some parameterized distribution, and you just compute the gradient with respect to f, and then you maximize it. And so basically this function, you can rewrite this function as the following. So basically, if you rewrite this is a strict equality. So basically, if you're maximizing the function f, if you maximize this function, you're maximizing the log likelihood of the data. If you're a dynamical systems guy, you would call that system identification. And at the same time, you're minimizing the KL divergence between the true posterior P and the auxiliary posterior Q. And that's actually pretty nice, because we assume, like the whole reason why we do VI instead of EM is because we can't compute the posterior. But if after we've maximized this, we have a distribution which is like very similar to P. So if we want to basically do posterior inference, we just do it on Q instead of P. And Q is usually much easier than P. And this is also how like the first connection to deep learning comes in. We parameterize our auxiliary distribution with a neural network. So basically, we choose some base distribution Q. So a Bernoulli, a Gaussian, like a fairly simple distribution. And then we assume that the parameters, so for example, in the Gaussian, it would be like the mean and the variance, or in case of the Bernoulli, it would be like the coin flip probability is some function of the input. And then we just approximate this some function with a neural network. So basically, we have a distribution, but the parameters are like a very complicated function of the input, of the observation. And then basically, we have a paper, like basically what we talked about I talked about that at the last American or like North American NILM stuff. And this is basically one example. So in this case, F is our neural network, psi are the weights of the neural network. And then if F is bounded between 0 and 1, this is a proper distribution. And you can enforce that it's bounded between 0 and 1 pretty easily by just using a sigmoid output. And now the next connection to dynamical systems. So appliances evolve over time. And basically, the temporal aspect needs to be modeled, and is actually fairly important if you don't want to overfit. So we assume that we can factorize the joint distribution, and now we have like this 1 to t, and t is like our last time step. We assume we can factorize that according to this, and this is basically the associated graphical model. And note that z is a vector, but this is not a factorial Markov model anymore, because we actually don't have the independence assumption. So if you do the same derivations and you derive f for this model, everything basically stays the same. You only have like, you introduce those dependencies on all previous time steps, but you just use a recurrent neural network for that, and you're fine, except for one thing. The joint distribution becomes intractable because of the dependence on all previous time steps. But the nice thing is, so this is still an inequality. And basically, if you maximize this, you're still doing a system identification, because this is just the chain rule factorization of the whole log likelihood. So if we maximize this, we're still performing system identification. So basically, the joint becomes, if you can derive the joint as this, it's fairly simple. And it's intractable for two reasons. First of all, this summation over the latent space is just intractable because there's exponentially many, like the domain grows exponentially with the number of appliances. And we need to compute the posterior. And we already know that the posterior is intractable. But like as I said before, we're gonna milk basically importance sampling and Monte Carlo integration. So basically, we can rewrite this as this. And basically, then we can evaluate this by sampling from Q. And because Q is a neural network, and we can fairly easily sample from that, but then we still have the problem that we need to compute the posterior. And the posterior is also intractable. So basically, the posterior is just the joint over the data like